Hello there guys, welcome back to another video on double integration. So this is a really cool one. So far with double integration, you may be thinking, or you may not, but you may be thinking, it's not too bad. It's just integration. I just got to draw some stuff sometimes. Sometimes I don't even have to draw anything. And yeah, it's just a double integral. It's just what it is. And I'm here to tell you that it's not going to get like crazy worse, but there's an extra dynamic that's about to appear that I've been concealing from you guys. There's an extra thing that you need to look out for and know that you can do. And it's related to what's called Fubini's theorem. So just take a look at this example integral, double integral, for a moment here. This is the integral of essentially cos x over x. In the x limits, we're going from 2y to pi over 2. In the y limits, we're going from 0 to pi over 4. So it looks a little bit crazy, but you could, maybe you're looking at it and you're thinking, I could probably do that, right? It looks quite similar to some of the previous ones that we've done. But there's one subtle problem with this that maybe the eagle-eyed viewers among you might have spotted. And that is that cos x over x doesn't have an integral. That's right, you can't integrate cos x over x. You at least can't express it as an elementary function. That means you can't write it as any combination of logarithms, trigonometric functions, powers, products, sums, differences, quotients. You can't really write it properly, is basically what I'm getting at. It doesn't have an elementary solution, so you can't integrate it. You can't integrate what's in the integrand. That's not grand. What are you going to do about it? Well, this is the cool thing about double integration that you can do. Fubini's theorem. So Fubini's theorem says that you can do this if you swap the order that you do the integration. So if you do dy and then dx, rather than dx then dy, you can maybe do it. So I'm not going to prove Fubini's theorem. I'm not going to even write it down. It's not really, it's just what it is, right? So basically what Fubini's theorem says is that it is possible to do the integration in a different order. You can swap them around, and I will show you exactly how to do that and to do this problem. So even though cos x over x can't be integrated, this double integral can be integrated, which is crazy because it looks like you need to do cos x over x first in order to get to the double integral, but you actually don't. This is the cool bit. So let's draw the region, guys. It looks like you don't need to draw the region, does it? Because they've just explicitly told you what the limits are. They haven't said it's a little r and then you've got to figure out what the region is, and like in the previous videos that we've done sometimes. No. They've just told you. So it looks like you can just immediately do it, but still draw the region. So let's draw the region, guys. Let's do it right here. So here's our x-axis. Here is our y-axis. So the first one is x. It's dx first. So that means that these limits, 2y and pi over 2, are functions of x. So the lower limit is x equals 2y. This is the same line, of course, as y equals a half x. So we can just consider a half x. I'm just going to draw a half x because they're the same line. And then x equals pi over 2 is the above one. So let's draw both of these. So y equals a half x is about roughly like that. Y equals 1 half x. And x equals pi over 2, maybe pi over 2 can be about here. That's pi over 2. And this is x equals pi over 2. Okay, so now we've got kind of triangle shape. Maybe we're bounded in the triangle. We don't know yet. Let's look at the y limits. So the y limits are 0 and pi over 4. So our y limits are y equals 0 and y equals pi over 4. So let's get those drawn on as well. So the line y equals 0 is the x-axis, so I won't draw that. Pi over 4, well, pi over 4 is going to have to be here because it's half of pi over 2, and this is the line y equals a half x. So hopefully that makes sense. It's going to go through, it's not a very straight line, guys, I know, but it's going to go through like that. So what part of this region, what finite part of this region is such that the x coordinate, or the x values within this region are bounded by basically x equals 2y and x equals pi over 2. Well, basically, left and right wise, what function is stopping, if I, for example, if I guess that it is this triangle for a moment, let's say that it's this triangle, and I'm just going to verify that it is this triangle. What function is stopping that region from spilling over to me? What function is it? Well, it's y equals a half x, or x equals 2y, right? That's the function that's stopping it from coming towards me. What function is stopping that region from spilling out that way? Well, that's x equals pi over 2. So that checks out, that's good. What function is stopping the region from going downwards? Well, that's y equals 0. What function is stopping the region from coming up? Well, pi over 4. Nice. You could also say that the function, this is an important note, you could also say the function stopping you from coming up is a half x, y equals a half x, right? But remember, on the outside of any double integral, you can only have constants, which means it can't be a function that's stopping you if you're on the outside of the integral. And once again, the reason why you can't have a function on the leftmost integral is because, of course, you won't get a constant as an answer once you get to the end of your working out, right? So you need to have a constant as your answer because you're basically finding a volume, is what you can think of this as. It makes no sense to have x's or y's in your answer when you are literally talking about what is a finite volume. Okay, so it is the line y equals pi over 4 that's stopping us from above. So the y limits are 0, pi over 4, looks good, and the x limits are 2y, pi over 2. Looks good to us. So it's definitely this triangle. This triangle is the region that we want. Once again, guys, we are not finding the area of this triangle. I wish we were. But actually we're finding the volume of a 3D shape that's coming out towards you into the direction of you, the viewer. Okay, so it's a little bit more complicated. What do we do next? Well, we could just do the integral, but again, we have this problem. We don't know how to integrate cos x over x. So why don't we do something very clever? This is Fubini's theorem. Fubini's theorem, once again, says that you can still evaluate this integral if you change the limits around. And this is the clever bit. So guys, watch closely. This is the clever bit. I want to rewrite this. I don't know what my limits will be yet. I can't just move the limits around. Cos x over x is still going to be here. That doesn't change. The integrand does not change. But I'm going to do, instead of dx dy, I'm going to do dy dx. Okay. So I'm going to actually go along the y direction first. Okay. I don't know what my limits will be, but I need to work it out. That's why I've drawn this region. Okay, so in the y direction, going from downwards to upwards, what is stopping me? Well, it's still the line y equals 0, stopping me from below. So the inside limit will be 0 again. Maybe you would expect that to happen because you've got a 0 there and a 0 there, so they are kind of swapping around. Perhaps you would expect that to happen. But this is where it differs. What did I say earlier? You could have the line y equals a half x stopping you from above, but it had to be a constant because it was on the outside. We're not on the outside anymore. So it can be a half x. So do you see how a half x doesn't appear anywhere at all in this original integral, but now it's there. So things are looking different already. Okay. What about the x's? Now these need to be constants because they're on the outside leftmost integral. So now for x, we're looking at constants instead of functions because we had a 2y earlier, that's a function of x. So we can't do that anymore. They need to be constants. So which x value stops us from coming towards me, this region? Well, the line x equals 0 is stopping us. And which x value is stopping us from going that way? Well, it's just x equals pi over 2 again. So now it will be 0 and pi over 2 on the outside. So this is the same integral. This is still the value, it has the same value. We're going to call it I still, it's the same integral, but it's different. The limits are different. Now you might say, okay, how does that help me? I still don't know what cos x over x integrates to. This is the cool thing. Yes, you do. Because we're integrating it now with respect to y. So because we're integrating with respect to y, cos x over x integrates to cos x over x times y, because it's a constant. You're integrating now, not an awful, literally unintegratable function, you're integrating a constant that looks a bit funny. So let's do it. This is the integral from 0 to pi over 2. Now, it's not something that we don't know how to do, it's something that we do know how to do. We're integrating with respect to y, not x. So it's cos x over x times y. Okay, now we're getting somewhere, and then we can put our limits 0 and half x in, 0 and 1/2 x dx. Okay, guys, hopefully that makes sense. And something really remarkable is going to happen. So, first of all, let's simplify this. We have integral 0 to pi over 2. Okay, and let's actually do this. So if we substitute y for 1/2 x, we will get cos x over x times 1/2 times x. Well, you can hopefully see the x's will cancel out, and we will end up with 1/2 cos x. Okay, if we substitute y and for 0, or 0 for y, this will all just become 0. So I won't write it, it's just all 0. So the whole integral is just this now. And I mean, you can see where this is going to go, right? It's going to be a nice result. So that's really cool. Let's finish the question first, and then I'll kind of geek out over it in a moment. So this is going to be cos x integrates to sine, so it will be 1/2 sine x from 0 to pi over 2. Okay, and then this is 1/2 sine pi over 2 minus 1/2 sine 0. Once again, guys, sine of 0, I'm not going to write it because it's just 0. So it's just this. Sine of pi over 2 is the number 1. So it's just 1/2 times 1, which is 1/2. And that's the answer to the entire double integral. So we can say that this is equal to 1/2 QED. So guys, the whole idea of this is that essentially you've taken something that literally cannot be integrated, but because you're integrating it with respect to a different variable, because you've done this Fubini's theorem craziness, actually it becomes something that's very straightforward to do. So we're going to do lots of these in the future, and you'll get a good idea of kind of where it comes about. But this is a very common thing that you can see. And basically, the reason why you can do this is called Fubini's theorem. Thank you guys so much for watching. I highly appreciate it, and I'll see you in the next video.